Okay, welcome to another session of Business Mathematics, Ugbs 202. We're continuing with what we started in the previous sessions. Today we want to look at some introductory ideas of financial mathematics, and gradually we are kind of finding our way into the main aspects of business mathematics. And so today we'll be looking at what we call cash flows. Now, cash flows basically just refer to the inflows and outflow of money over some time period, right? And it's basic. At some point in time, you get some monies. At some point in time, you also part with some sums of money, and it's a normal phenomenon in life. Businesses make expenditure or make expenses, and they also make revenues. And so we want to just analyze this idea of cash flows. But there are two ways in which, or two tools we use to analyze cash flows. We have what we call the cash flow tables and then the cash flow diagrams. Well, but I think you guys are too smart for me to teach you what a cash flow table is, because it's only a schedule. It's only a table that indicates a period and then some amount of money going out and coming in. So that would be too easy to teach. So we'll rather deal with the cash flow diagram, which is not complex at all, very easy to analyze, to understand. And so take a critical look at the diagram I have on the screen. Now let's try and break it down gradually. This diagram is referred to as the cash flow diagram. We're going to explain it one after the other, and you understand what it means by and how we use this cash flow diagram. This line here, which looks like the normal number line that we've known from our primary school days, we will not call it a number line, but we'll call it a timeline of money. It just gives us specific periods within which we are supposed to, or we are trying to evaluate the flow of money, right? And so we have 0, 1, 2, 3, 4 in that order to some period n, or some future period. Good. Now, period 0, we will always refer to it as the present period, or let's say in some layman's term as today, right? Any other period apart from period 0 would be considered as a future period. And so supposing that this timeline of money is in years, and then so if I am here today at period 0, then period 1 would be 1 year from today. Period 2 would be 2 years from today, and it follows in that order to period n. Okay, now we represent cash flows or sums of money that come in and out with arrows, either pointing up or down. Now think about it like an idea of an injection and then a leakage. Now if you have an arrow pointing up, this is more like an inflow. It is assuming that money is coming in. So an arrow pointing up represents some sum of money coming into your business, or probably coming into your account, coming wherever you keep your monies. And if you have an arrow pointing downwards, that represents some sum of money leaving your coffers, and we'll call that as an outflow. And so arrows coming in are inflows, arrows going out are outflows. The length of the arrow is dependent on the value or the sum of money you are actually trying to represent on the diagram. Now, for instance, if you're representing 10 CDs and then 100 CDs, it is just, let's say, reasonable to just draw the arrow of 10 CDs shorter than the arrow of the 100 CDs. And so the length of the arrow is just, you just determine it, but just distinguish it clearly that the sum determines the length of the arrow. So now let's try and understand these things. Period 0 here, and then between period 0 and period 1, okay, so let me not call it period yet. Between 0 and 1, we'll refer to that interval as period 1, right? So for instance, taking my arrow here, from here, this point to this point, I'll call it period 1. And it follows in that order. This point here is the beginning of period 1, and then here would be the end of period 1. But this same point will be the beginning of period 2, and here would be the end of period 2. I hope you're following. So you see, that's why I'm trying to use these arrows here to, so this interval is period 1, this interval is period 2, this interval is period 3, and follows on and on. This is the beginning of period 1, this is the end of period 1. This again will be the beginning of period 2, which is the same as the end of period 1. And here, this will be the end of period 2, but the beginning of period 3, and it goes on and on and on like that. And so that's how we explain, or we kind of analyze, what's it called, a cash flow diagram. Let's see. Good. So what I have here, this table here, is a cash flow table. That's why I said it is not possible to teach a cash flow table, because it's too easy. I can explain this to honorable university students, saying this is how we draw. Okay, so this is some data that is being represented in a schedule or in a table like this, which we call the cash flow table. We can take this information and represent it on a cash flow diagram. So let's see how we work on that. Okay, so now period 1, 2, 3, 4, 5, 6, 7 have different sums of money. Now period 1 has minus 100 million, period 2 has 10 million, period 3 has 10. Okay, so period 2 is minus 10 million, and it follows in that order. Where you have the negative, it is just another way of saying that that is an outflow, right? That is some money leaving your coffers. The positive value is what we call the inflow. Well, in some other expressions or in some books, you would find out that these values will be written in parentheses, indicating that they are values that are leaving your coffers. And so here, if I want to represent this on my timeline of money, if I draw my diagram, my timeline of money, and probably I have period 1, because this is minus 100, I would draw this arrow downwards and write minus 100. Now period 2, which is this, I'll draw it downwards because it's minus 10. Now you do see that 100 and then 10 do not have the same length, right? The 100 is longer than this one. That is how I chose to do the length. So it is just up to you. The length of the arrows is just dependent on the value that you are trying to represent. And the others, because these ones are positive values, we see they are inflows. We kind of just introduce them upwards like this. So now let me just introduce a basic idea. Now, in real life situations or in business instances, you receive monies or pay monies sometimes at the beginning of periods or sometimes at the ends of periods. Workers are paid salaries in Ghana at the end of the month. Well, if you owe a bank a certain sum of money, they deduct at the beginning of the month because that's when they know you have money in your bank. And so cash flows could occur at the beginning or at the end. Either ways, we can represent such information on the diagram. Now, for instance, let's take a typical example as this one. So now that you've understood how we draw the diagram, let's go back and now answer it appropriately as the question demands. It says that now let's represent this information here when money is paid and received at the beginning of the period. You remember when I was explaining the diagram and I said this entire interval is period 1. This is the beginning of period 1 and this is the end of period 1. Okay, so if we come here and we are saying that money is being paid and received at the beginning, this entire interval is period 1. And so here, this value here would be the beginning, right? And so you notice that in this diagram, instead of starting from 0, we actually brought this 1 here. Is that okay? And so here, because it's at the beginning, you see, this is period 2, and this money is being paid at the beginning of period 2. This is period 3. This interval here is period 3, and then the 10 million is occurring here, and in that order. You will notice that when you're doing the payment at the beginning of the period, your arrows do not get to the end. It will look as if you are short of 1 point, but that is not the case. It is just, it makes complete sense. It makes absolute sense because we said this is the beginning of a period. This is the end of that same period. And this same end is the beginning of the next period. And so Do not be worried if you're representing it at the beginning and then it looks as if you did not end at the exact end. It is correct. Now, if we were assuming that the payments were being made and received at the end of the period, then you notice that this interval from here to here will be period 1, and this will be the end of period 1. And so our first value, which is 1 minus 100 million, will occur here, right? And then the others will follow. And so because we are paying at the end, you will notice that your last value here, which is 50 million, will come to this point. Okay. All right. So now, why would we be interested in the time value of money? Why would we want to evaluate what happens to money over time? Well, there are some economic conditions available that, well, they necessitate we doing this analysis. Now, for instance, if you have an issue like depreciation or inflation or opportunity cost and all that. Now, for instance, money today would not be the same as money tomorrow, isn't it? If you have 10 cities, or what I'm trying to say is, what 10 cities would afford today, well, give it 10 years to come, I'm not too sure 10 cities will afford the same quantity. Of course, take a ball of kenkey. Funny example. If 2 years ago you could buy 2 balls of kenkey with 1 cedi, hello, in Ghana now you can now buy just 1 ball of kenkey with 1 cedi. That's if you are lucky. Okay, so you see, so for such instances, you should understand that, well, money would not remain the same. Now you take issues as depreciation. Well, an asset over time would not perform efficiently as it would have performed or it was performing when it was bought new. Take a typical example of a car. If you buy a car today and use it for 4 years, you don't expect to sell it at the same price at which you bought it, because over the years it has deteriorated, and that is what we call depreciation. And so these factors actually necessitate we analyzing what money would be today and tomorrow or within some time space, so that it helps us understand or make appropriate decisions. Now you should understand that this is business math, and businesses have their sole motive of maximizing profits, and so any decision they would make regarding their funds, they would want to make the best decision as much as possible. Okay, so why would we want to do this? There's a relationship between this, the present and then the future. That is why we actually evaluate this thing. Now we say that because of the time value of money, the present value of a future amount of money, I'll take this again. Now, because of time value of money, the present value of a future amount of money and the vice versa is of great importance in business. See, now, so say because, for example, if you have invested 1,000 cedis in an asset that offers an interest rate of 20% per year, you will be interested to know today what you will receive the next year. Now, think about it. Even in my case, I think I have gone ahead of time. Now, if you're going to do some investment, you would want to practically know how much you would get at the end of the investment period, isn't it? That is evaluating the value of some amount in the future period. That is like considering the future sum of a present value. And so because of these issues, you would also want to know or kind of understand these relationships. Okay, so, well, we will try and evaluate these things over time and kind of try and understand how we compute future values and then present values, and then we'll move forward from there. Okay, so like I was saying, now, all this while we've been trying to understand this relationship between the future sum and then the present sum. One basic formula underpins this entire idea. Now, basically, just have this at the back of your mind, that if we want to find the future sum of a certain amount of money, let's say today I have a certain sum, and I want to know how much that sum is going to be someday in the future. This is just the basic expression that helps us actually identify that. And in fact, this expression forms the basis of everything we are going to do from this point onwards. And so just have this formula at the back of your mind. It's not like memorize it, because it's nothing exceptional. Now, if I have this expression, F, which is my future sum, which I am looking for, equals P, which is my present value, into bracket 1 plus I. I here is the interest rate, or the rate at which my sum would be growing. And then N is the number of periods, or how many years or wherever I'm doing the investment on. Now, this expression here tells the exact relationship between the present value and then the future value. Now, given this expression, I can also find my present value given the future sum. Let's take an example. For instance, if today I have 100 cedis and I do not want to spend it, and I walk into any bank and it says they'll give me a certain interest rate, and so I should just keep my money with them for 5 years. What I'm doing here is to say, if I use this expression, I'll ask myself, how much is my 100 cedis going to be after 5 years? It means that I am interested in knowing the future equivalent of my present value, which is 100. And so my F turns out to be 100 cedis, which is how much I have now. That's why we call it the present value. This one is a constant. Plus, let's say, well, normally Ghanaian banks are generous. They'll give you 3%, 0.03. And probably they said for 5 years. I guess you can easily compute this. And so whatever I have here would give me the future equivalent of 100 cedis at an interest rate of 3% for 5 years. Now, how about, let's say my daddy would be going on pension in some years to come, and he says that, well, when he goes on retirement, he'll give me, let's say, 2,000 cedis. Now, if I want to find, now, maybe 2,000 cedis, if my daddy will keep his promise and will not change his mind after retirement, then maybe I would be interested in knowing how much 2,000 cedis will be worth today. Maybe I could take a loan in place of that 2,000. So when 2 years come, I would actually go for the money and pay for it. I can rewrite this expression to find the present value of a certain future sum, which I know of, but I do not have it. So let's see. All I want to do is to make my F the subject. Sorry, make P my subject. Now, I am interested in P. I know of my future sum. So my P will now tend to be what? F over 1 plus I to the power n. What did I do? All I'm interested in is to make P stand on its own. So I divide both sides by this entire expression, right? And so that gives me my P. And so, for instance, I know this future sum, like my daddy says, he will give me 2,000 cedis. And so probably if I'm supposed to go for a loan from a bank and say, well, in 2018 from today, my dad will give me 2,000 cedis. So at what interest? Maybe they'll give me 3%. So I do the same computation for, let's say, 2 years. And whatever this expression would give me would be the present equivalent of what? These 2,000 cedis. And so these two expressions will form the basis for whatever we are going to do. If you want to find the future sum of a single amount, this is the expression. If you want the present value of a single amount, this is the expression. Okay, so let's continue and look at types of cash flows. Okay, so we want to continue with the types of cash flows that we have. Now, monies come in and out of businesses in various forms. We're going to look at 3 types of cash flows. Well, in fact, we'll look at the 4th one, but it doesn't really come too often. But the first one we want to look at is the uniform cash flow. You know, when you have a specific sum of money that comes in or goes out over some time period, we refer to that as a uniform cash flow, where in this case the emphasis is on the sum that is coming in or going out. The sum coming in or going out is the same. So for instance, let's take a typical example of a loan you have taken from a bank. Now the bank makes certain deductions from your account every month, isn't it? Now, for instance, they could be taking 1,000 cedis from your account every single month. Now for, let's say, 5 years or 10 years or 20 years, if that 10 cedis is going to remain the same every period that they do the deduction, then that type of cash flow, we'll refer to it as what? A uniform cash flow. The sum going out is the same. It also happens in some instances. Now, to you, it's a cash outflow, but to the bank, it becomes an inflow because they will be receiving from you and you will be losing. So either ways, it becomes an inflow and a cash flow. So let's look at from the slide. I try to have a diagrammatic representation of that idea, where A is that same amount. You notice that all my arrows are at par; they are the same. So let's take an example. So supposing this is an instance where we have 5,000 being the cash inflow for some number of years. Well, we can actually solve this using the same. Now think about it. On my timeline of money, this is period 0. Like I said from the beginning, this period 0, we can assume period 0 to be today. Any other period apart from 0 is a future period. Okay, so 1 is in the future, 2 is in the future. So we can easily say that all these sums are in the future. Now, if I want to evaluate how much this would be today, I could easily do the same thing I just did, right? It's just like finding the present value of some cash flow. So I take 5,000, I do 5,000 over 1 plus 0.05. So I'm assuming that my interest rate is 5%. Just putting it into perspective, what I just did before using the marker, where I said in finding the present value, P equals F over 1 plus I to the power n. My F is this future value. If I'm here today, any other period is in the future. So this value becomes my F. This is my I. And then the n is the period. Now think about it. This is how we calculate the n. Now if I'm here, how many steps do I have to move from this point to this point? I'll move only once. So here, for the first instance, my n is 1. Now if I'm here and I want to come here, I would have to move 1, 2. I'll move twice. And so my n is 2. So it goes on and on and on like that. Okay, so I can do the same. But you see, this is quite tedious. In fact, how about I give you a similar cash flow which says that you're receiving the same amount of money for 70 years. You're going to do this 70 times. That is barbaric, right? And medieval to me. So I think we can easily come out with some basic expression. You see, that's the beauty of business mathematics. You see, we adopt mathematical principles and bring them into our daily business activities. And so we can come out with a basic formula that can help us deal with this thing. And so when the periods or the years become many, using this individual approach becomes quite difficult. And so there is a basic expression. In fact, we can derive it, but well, we'll take it down and we'll see how it works out. So when the cash flows become enormous, or the period becomes so long or so huge, we have a basic formula. And so it is expressed as this. So for a uniform cash flow, so this is what we say. If you are finding the present value for a uniform cash flow, what we have is A over I. You open a big parenthesis and you do 1 plus I to the power n minus 1, all divided by 1 plus I to the power n. Then you close the parenthesis. Now, this expression here helps us to find the present value for a uniform cash flow. So I'll do my P will be equal to this. Now let's explain this. Now A would be, or A is that uniform sum that keeps coming in or going out of your coffers, right? So from the cash flow diagram we had just 5,000 cedis going out throughout. So our A would be that 5,000. Now the I is the interest rate, which obviously you would see it. And then N, because this is supposed to be a shortcut that should evaluate the entire period, our N is going to be the entire number of periods. So supposing this is supposed to have been going on for 10 years or 20 years or 100 years, N will be the total number of years. Now this expression, please be careful. This 1 minus 1 is not N minus 1. It is this whole expression minus 1, right? And you divide by this expression. Then you're done. So you just, if we had, from our expression, we had 5,000 being the uniform sum divided by our interest rate was 0.05. I open my big parenthesis, then I open a small one, and I have 1 plus 0.05. Then how many years? It was for 6 years, and so my n is 6. Then minus 1. Then I do the denominator, 1 plus 0.05 to the power 6. Good. So once I do this, I break this down, I break this down, I break this down, and put everything together. It gives you one answer. It saves you a lot of time and trouble, where you would rather have to take 5,000 and divide it by 1 plus 0.05 to the power 1 and do it for how many number of, or the entire number of years that's the question, or the years you are doing the evaluation. Okay, so let's continue. So from what I just did, this is how it continues. So because my 5,000 becomes the same amount coming in and out, well, my A is the 5,000 divided by the interest rate. Then I do it with this, I do that, and this is what I get, 25,378.46. And I think you should also try it at home and see it. Okay, so now let's look at another example. For this, the idea is the same. I'll just walk you through. Think about it. How are you going to deal with this problem? You have a uniform flow from period 1 to period 3. Then it jumps up to a certain high value. Then it falls back again to another uniform flow to the end of the period. Well, this is easy. You could use a number of ways to do it, but let's keep to a more conventional and a more safer approach. Like we do it step by step. It doesn't hurt. Okay, so I want to evaluate all these cash flows and find the present values. What I do here is, you see these three, it is 2,000, 2,000, 2,000 flowing over, or the same amount flowing over a period of 3. And so I'll take all these and bring it to period 0 using the shortcut or the formula that I just introduced you to. Okay, so when I take this, I bring it to period 0. I keep it there and wait for the others to join. And so then I come here to the other one. Now look at these other ones too. 4,000, 4,000, 4,000, 4,000. All of these are also uniform. I'll take these and then put them in the same formula like I did. But the good news here is, if you do this, it will not take you exactly to period 0. It will bring you to this period. So this brings us to a certain caveat using this formula. Now, from the derivation of this expression using this formula, it says that when you find the present value using this uniform cash flow approach, it brings you to the period immediately preceding the beginning of the cash flow. And so if this period is not necessarily period 0, then you would again have to carry it as a single sum and take it to period 0. Think about it. We are moving from period 5 to period 8. Now, the period preceding the beginning of this cash flow is period 4. And so if we use this formula, it will bring us to period 4. Now, we will now have to take that value as a single sum and take it to what? Period 0. Now, but think about it. If I take these and I put it into my formula, and my n is going to be 4 years because they are 1, 2, 3, 4, it brings me to this period. Now, in period 4, there is already some value there, which is 7,000. And so whatever you bring from this computation, you sum it or you add it to this value here, and you take it as a single value and bring it to period 1. So let's go through the solution so you understand. I took 2,000, put it into the expression, and you have this expression. You have this. So here, if I put all these three values together and I bring it here, the present equivalent of these three is 5,446.5. I'll keep it here and go for the others. Now, the rule says that when you use the formula, it takes you to the period immediately preceding the beginning of the cash flow. And for this case, we are lucky. The period immediately preceding the beginning of the cash flow is period 0. So we will not have to do any more carrying. So it brings us automatically to 0. But this one here brings us to period 4. And so when you put 4,000 into the expression for 4 years, we have 14,183.8. This value comes up here. But in this period, there's a value already there as what? 7,000, right? And so I add 7,000 to 14,183.8. And what do we have? We have 21,183.8. Now, that is a single value. So if you want to find the present value for a single value, you remember the formula. P equals F over 1 plus I to the power n. And so I take my 21,183.8 and I divide by 1 plus 0.05. Now, how many steps would I move from this point to 0? I'll move 1, 2, 3, and 4. And so you can see that the years here are 4. And so when I discount this, I have 17,247.96. Now, the total present value for this entire cash flow will be the sum of all the values I have brought here. The total from this point was 5444.6.5. The total from this and this put together was 17,247.8. And so when I put the two together, I have 22,694.46. Okay, so the second type of cash flow we would also look at is the arithmetic gradient cash flow. This is the kind of cash flow where the sum or the monies that is going out or coming in is increasing by a certain fixed sum. Look at the diagram I have here. I have a certain sum, say A. And then A increases by a fixed sum K. And so over the years, it keeps increasing, it keeps increasing, it keeps increasing by K till the last period. And so here, this is quite a little build up on what we have seen before. But it is easy. You can deal with this in a very easy way. See, if I cut this section off, all these values would have, all these cash flows will have the uniform sum of A, isn't it? Because, for instance, assume that I have a value 1,000 cedis. Every year, increase whatever you have, the initial payment, by a certain fixed sum, let's say 50 cedis. So if year 1, you pay 1,000, year 2, you will pay 1,000 cedis plus 50 cedis. Year 3, you will pay 1,000 cedis plus 50 plus 50. Year 4, you pay 1,000 cedis plus 50 plus 50 plus 50. So that 50 is what I'm referring to as the K. And so here you pay 2 times the K. Here you pay 3 times the K. Here you pay 4 times, and it goes on and on and on like that. Okay, so here if I cut from here my A, I would have that 1,000 cedis or that uniform sum. So all I have to do with is the increment, the increasing fixed sum. And so by computation or derivation, if we want to evaluate this entire cash flow, what we normally do is we'll say the total present value will be PA plus PK. We know PA already. PA is the uniform cash flow, what we just did. A over I into bracket 1 plus I to the power n minus 1, all divided by 1 plus I to the power n. That is our PA. Now, our PK, which is from here, K, 2K, 3K, 4K, n minus 2K, it goes on and on and on. This, if we actually derived a formula for it, this is what we end up having. K over I squared 1 plus I to the power n into bracket 1 plus I to the power n minus n I minus 1. Quite a cumbersome formula, but well, you see, you get used to it as we use it or we practice it. So, but remember here that our k is only this increasing sum, and then our a would be for this one. So let's see if we can have a basic example here. So I have a certain cash flow. It says find the present worth of the cash flow that begins with 3,000 cedis in the first period and increases by 500 per period for 10 years with interest rate of 5%. Interesting. And so in the first year, I pay 3,000. The second year, I'm not going to pay 3,000. I must top it up with 500. So I'll pay 3,500. In the third year, I'll pay 4,000. And it goes on and on and on and on. And so you notice that my increment is in a fixed sum of what? 500. So here, we say to find the total present worth, we do our PA plus PK. All we are saying is we kind of try to divide this cash flow into two parts, like we did in the diagram, where we take the A part, so we would have a uniform cash flow for all the A's, and then we'll just work on the individual increases. So for my PA, the initial amount we pay is 3,000, and you can all see 3,000 will be common to all the years. And so we'll calculate for 3,000. You see that the period immediately preceding the cash flow is 0, so you don't have too much problem. Once we evaluate it, it brings us to period 0. Then we now take the second part, which is PK, and put it into our expression, K divided by I squared, 1 plus I, goes on and on. And so our K, in fact, the only thing you need to know is the K, which is the constant increment. The rest is obvious. Our I is the interest rate. Our N is the period. And it goes from this period, from period 2 to this one. And so you just take it back and bring everything to our present period. And then we sum the two totals. And that's just it. It's no big deal. So you can easily do this. We just go through the process step by step. And one thing, when you're doing the computations, please do take your time and do them individually. Board mass, bracket first. If you do not know how to impute this in your calculators and you punch everything without doing the brackets or the parentheses well, you end up getting the wrong answer. So I personally advise that you do it gradually. Take this one, find the square of this, multiply it by this, then divide by this, keep it outside and go. But well, do it as you please. Just make sure you don't have the wrong answer. Okay, and then the final cash flow that we want to look at is the geometric gradient cash flow. For this type of cash flow, where in the previous instance we have the cash flow either increasing or decreasing by a fixed sum, here the cash flow actually grows or decreases by a fixed percentage, and which we will call the gradient or the growth in which, and so that growth is in percentage, and this is how we express it as 1 plus 1 minus all this expression. Good, but there are two instances. When the rate at which the cash flow grows is different from the interest rate, we use this expression. And so we say when G is not equal to I. So for instance, if your cash flow is supposed to be growing by 12% and then your interest rate is 10%, G is not equal to I. And so we use this expression. But when your cash flow grows at a rate which is the same as the interest rate, let's say your cash flow grows at 10% and then your interest rate is also 10%, we use this expression, A into bracket N over 1 plus I plus this. And then I think there's nothing different here. Your N is still the number of years. Your I is the interest rate. If you come back to this one, G is the rate at which the cash flow is growing. And then I is the interest rate of the cash flow. Okay, so just a basic example here. Then we draw the curtains on this session. Now, for instance, say the academic fees of University of Ghana is set to increase by 10% per year for the next 4 years. you are a first-year student and the fee is 1,000 cedis this year. Your guardian would be traveling, so yeah. So he wants to put a fund down for you that will be sufficient to pay your fees for the total 4 years. So how much should your guardian deposit today if the fund pays interest rates of A, 10% and B, 5%? So look at this instance. Your A is 1,000, G is 10%, I is 10%, and N is what? 4. Now here, you do see that the G, the rate at which the academic user fees or the school fees is growing is 10%. And then the fund in which your guardian wants to put the money for you is also 10%. So your G is equal to your I. And so we use the simpler version, which is a 1,000 into bracket, the number of years, which is 4, then 1 plus I. That will give you whatever it should be. But in the instance where your G is not the same as your I, it means that the rate at which the academic fees is growing is 10%, and then the fund pays 5%. G is not equal to I. We use the more elaborate expression, and we have this value. Okay, I hope you enjoyed the session. I'll see you again in the next session. Thank you.